Hello friends, in this video we are going to study about the compensators in the control system. That what are the compensators, what is the use of compensators in the control system and why we require the compensators in the control system. So let's start with our topic. As we know that the main requirements of a control system are accuracy, speed of response and stability. That is, we require that a control system should be accurate, it should be stable and it should have fast speed of response. So the main performance specifications for a control system, they become accuracy, speed of response and stability. Now it may happen that because these are the ideal conditions, accuracy, good accuracy, that a system is an accurate, stable and fast speed of response. These are ideal situations. In practically, we don't get such a system which is accurate and stable and at the same time it is having fast speed of response. So in those cases, we need to have some mechanism or some method so that we can convert this unstable system into a stable system, or we can convert an inaccurate system into a more accurate systems, or we can improve the speed of response of the system also. So the main basic idea about this compensator is that what we want, that a system, a control system should meet these performance specifications. That is, it should be an accurate system, it should be stable and it should have fast speed of response. So the main performance specifications for any control system are accuracy, stability and speed of response. So sometimes we have to convert or we have to compensate an unstable system to a stable system, or we want to improve the stability of the system also, so that overall what we are doing, we want that our system should meet these performance specifications. So in order to meet these performance specifications, it is required to redesign the system. Redesign means that we have to either add or we have to eliminate some component of the system, or we have to make such adjustments in the system so that the overall system, it is giving these, or it is having these performance specifications. Okay, so one of this redesigning is that we are adding an external device to the system, and this external device, this technique of redesigning the system so that it meet these performance specifications, is known as compensation. Okay, so an external device, what we do in this redesigning, we add an external device to the system, and this technique of adding an external device to the system is known as the compensation of the control system. Compensation is nothing but it's a type of control action which is performed on the system. So another name is control action. Okay, so this technique of redesigning is called the compensation of the control system, and the external device which is added to the system is called the compensator. So this is why we required a compensator or a technique of compensation in the control system, so that we can make our overall system, or we can have a system which is stable, plus it is accurate, and it is also giving good speed of response. Okay, so to meet these performance specifications, we are doing this compensation of the control system. Now, how we can do the compensation of a control system? Compensation in a system can be achieved by the following ways. The first way is by reducing the steady state error. So, steady state error. Now, how we can reduce this steady state error? It can be reduced by increasing the forward path gain. Okay, so we can reduce the steady state error by increasing the forward path gain, and we can introduce the compensation in a system. But while doing this, if we increase the forward path gain, it will make the system unstable and it will become oscillatory. Okay, so this is the disadvantage of this point, that if we want to reduce the steady state error by increasing the forward path gain, the system becomes unstable and it becomes oscillatory. So steady state error, it can be reduced by increasing the forward path gain, but it will make the system unstable and oscillatory. So we cannot use this way to introduce the compensation. Second way is introducing a compensating network. And this introduction of a compensation network, it is nothing but the addition of poles and zeros in the transfer function of the system. Okay, so first method was reducing the steady state error, which we have seen that we cannot do this because it makes the system unstable and oscillatory. And second way is the addition of poles and zeros to the transfer function. So let's see that what will be the effect when we add a pole or zero to the transfer function of the system. What is the effect of it? First we will study that what is the effect when we add a zero to the system. So the addition of zero to the open loop transfer function will first is lead the system towards stability. So if we add a 0, the system will become more stable. So it is a good point because we want that the system should be stable. So this is the first effect. Second is the speed of response becomes fast. So this is also a good point because we want that our system should have fast speed of response. It should fast, or we can say that it should quickly respond towards the input. So this is also a good point. Now third point is that the accuracy is reduced. Now this is not desirable because we want that our system should be accurate. So these are the two good points when we are adding a 0 to the transfer function, and this is our negative point that the accuracy is reduced. Now let us see that what will be the effect when we add a pole to the transfer function. First, if we add a pole, then the system becomes unstable. So it will lead the system towards instability. Second, speed of response slows down. This is also a negative point. Third is accuracy increases. So this is a good point when we are adding a pole. These two are negative because the system is becoming unstable. It is leading towards instability, and speed of response, it is also slowing down, and accuracy is increased. So if you see that if we add a 0, system is stable, speed of response is fast, only accuracy is reduced. And in this case, the system is unstable, speed of response is also slow, but accuracy is increased. So there are negative and positive points in both the things. Like if we add a 0 and if we add a pole, then we can have negative points in both the things. So what we do in the redesigning of the control system, or while introducing a compensating network, we will add these poles and zeros at suitable places so that there will have we can say that they are having a effect in some desirable form, like stable. Also the system also becomes stable, speed of response is also increased, and accuracy is also increased. So we will add these poles and zeros in some proportion, or we can add them at suitable places so that this overall the system performance is improved. So for the design of the system in the S domain, introduction of poles and zeros at suitable places will give us the specified performance or desirable performance. Okay, so what we are doing, that is in the compensation of the control system, what we are doing, we are introducing the poles and zeros at suitable places so that the overall system performance is improved. Okay. Now, main requirements are accuracy and stability. Speed of response is not of so much concern. We want that the system should be accurate and it should be stable. Okay, so main requirements we want is accuracy and stability. So stability is improved due to the addition of 0, and accuracy is improved due to the addition of pole. Okay. So this can be achieved by adding a system or adding a network between the error detector and the plant. If you see the block diagram of a control system, first we were having this as the error detector, then we have the plant, this is our output, and it is our feedback. So the transfer function of the plant, it is GS, and the transfer function of the feedback loop is HS, and this is our error detector. Don't consider this block. If you consider this is the general block diagram of a control system. Now here we are adding an external device between this error detector and the plant, and this is the compensating circuit. So we are adding this compensating circuit between the error detector and the plant so that the system gives us a desirable performance. So we can say that the definition of the compensating network is that the device which is added between the error detector and the plant is known as the compensating network. So the network which is added between error detector and plant, it is known as the compensating network. Now there are different arrangements for the introduction of these compensating networks in the system. Like here we have added the compensating network between the error detector and the plant. Now they can be added in series, they can be added in parallel, or in feedback also we can add. So there are different arrangements of the this compensating network. So let us study these arrangements one by one. First arrangement is the cascade or series compensation. Okay. So when a compensating network, it is added in series or it is inserted in the forward path, then that arrangement or that type of compensation is known as cascade or series compensation. Okay. So if we write the explanation of this, that when a compensating network it is inserted in the forward path, this is called series or cascade compensation. Now if we draw the block diagram for this, this is our input RS, this is our output CS, this is our compensating network, and it is the fixed element, or we can say plant. So we have added the compensating network in the forward path, so it will be called as cascade or series compensation. Now next type of compensation is feedback compensation. Now in feedback compensation, if we are adding the compensating network in the feedback path, then that type of compensation is called the feedback compensation. So let's, in this technique, so in this technique, the signal is feedback from some elements and the compensator is placed in the resultant inner feedback path. And that is why, because here we are adding the compensator in the feedback path, the signal is also feedback through it. So it is also known as parallel compensation. Let's draw the block diagram for this. This is our input. This is the fixed element. So this output signal, it is feedback from this compensating network. We are connecting the compensating network in the feedback loop. Also we have the feedback signal to this error detector also. So because it is connected in parallel to this plant, so this is also known as parallel compensation. Okay, so this is the second type of arrangement of the compensating network. Now third type is load compensation. In load compensation, we are combining the series and the feedback compensation. So it is a combination of series and parallel compensation. Okay, so we are combining the series and feedback compensation in the load compensation. So let's draw the block diagram for it. So load compensation, it is the combination of series and parallel combination of feedback compensation. If we see, this is the series compensation, and if we see this, this is the feedback compensation. So combining these two, it will become load compensation. So these are the three types of arrangements for introducing the compensating network in a control system. Now let us study the various types of compensating network which are available to us and which we frequently used in a control system. So compensating network, there are various types of compensating networks in a control system. So let us first define the compensator. That what is a compensator? A compensator is a physical device which may be electrical network. So what is a compensator? It is a physical device which may be an electrical network, a mechanical network, or it can be a combination of various types of devices. And what this compensator is doing, it is allowing it is making some adjustments in the system so that the overall performance of the system is improved. Now, there are three types of compensating networks. Three types of compensating networks which are this based on the electrical network. So, there are the following: electrical compensating networks are generally used in control systems. The first is phase lead compensator. Second, we have phase lag compensator. And third is phase lag lead compensator. So these are the three electrical compensating networks which are generally used in the control systems, and they provide the compensation in the control systems. So let us study that what are the basis of these phase lead, phase lag and phase lag lead compensators. Okay. Now, when a sinusoidal signal is fed as an input to the control system, so the output, it may have some phase difference with the input. Okay, input is a sinusoidal input, so the output will also be a sinusoidal output, but it may have some phase difference with the input. Now, if the phase is leading, then it is called the phase lead compensator, and if the phase is lagging, then it is called the phase lag compensator. So the basis of this difference between these compensator is the phase difference between the output and the input of the system. So when a sinusoidal signal Okay, so when a sinusoidal signal is fed to the input of a network, a sinusoidal steady state output which is having a phase is obtained. Now, when the phase is of the output voltage, it is leading the input voltage, then it is called the phase lead network. When the phase of output voltage leads the phase of input, the network is called phase lead network. Okay, and when the phase of output voltage is lagging the phase of input, the network is called phase lag network. So this is the basis of division of this phase lead and phase lag network, and on this basis only the phase lead compensator, phase lag compensator, they are defined. So let us study these compensators one by one, that how they affect the control system or how they improve the performance of a control system. The first compensator is phase lead compensator. So let's start with the first compensator, phase lead compensator. In phase lead compensator, the phase of the output voltage, it leads the phase of the input voltage. It means that whenever we apply sinusoidal input to the phase lead compensator or phase lead network, the phase of the output voltage will lead the phase of the input voltage. Here, as we are considering the electrical compensating networks, so let us consider an electrical phase lead network. Let's draw the diagram or circuit diagram for this. So this circuit is an example of a phase lead network. Here the phase of the output voltage, that is E0, it will lead the phase of the input voltage, that is EI. Okay. Now to derive the transfer function, let us apply the Kirchhoff's current law at this node. So the Kirchhoff's current law or KCL says that the algebraic sum of the currents at a node is equals to 0. So algebraic sum will be equals to 0. So here we will consider I equals to I1 plus I2. So to derive the transfer function, apply KCL. So we will get I equals to I1 plus I2. Okay, because at this node the incoming current is I and the outgoing currents are I1 and I2. So incoming current will be equals to the sum of the outgoing current. So I will be equals to I1 plus I2. Now I here it is equals to the current flowing through this resistor. So the voltage drop, if we calculate the current across this resistor, it will be equals to I. So here we can write this as E0 upon R2. I1 it is equals to 1 upon R1, that is the current across the resistor R1, and the voltages they are subtracted, that is EI minus E0. Similarly I2 it is the current across the capacitor. So current across the capacitor is C dV by dt. So here C is the capacitance and d by dt. Here we have the difference of the input voltage and the output voltage. So this is the equation which we have obtained. Now taking Laplace transform on both sides of this equation, we will get the Laplace transform of E0 is E0 S and 1 upon R2 is as it is. Here we have 1 upon R1. Laplace transform of EI is EIS minus E naught S plus the Laplace transform of C d by dt, and this difference of the voltages will be SC and difference is EIS minus E naught S. So we have obtained the Laplace transform of this equation. Now we have E naught S and EIS. So just combine the terms which are having EIS and E naught S, that is combining all the coefficients. So we will have E naught S 1 upon R2. Here we have minus 1 upon R1 and here we have minus SC. So this will come on the left hand side and minus sign will become plus sign. So 1 upon R2 plus 1 upon R1 plus SC. Now similarly on the right hand side we will have the coefficients of EIS. So here we have 1 upon R1 EIS plus SC EIS. So EIS okay, SC plus 1 upon R1. Now we want to find out the transfer function. So transfer function is the ratio of the Laplace transform of the output upon the Laplace transform of the input. Now here the output is the output voltage E naught and the input is the input voltage EI. So Laplace or we can say the transfer function is the Laplace transform of the output voltage upon the Laplace transform of the input voltage. So here we will take the ratio of these Laplace transform of the output and the input voltages. So it is E naught S upon EIS So this is the ratio of the output and the input voltages Laplace transform. Now let's simplify this transfer function. Now in this ratio take C as common, okay, on both the numerator and the denominator. Take C as common. So when we take C common from both numerator and denominator, it will be cancelled out and we are left with in the denominator we will have S plus 1 upon R1C plus 1 upon R2C. Now take the LCM. We have S plus 1 upon R1C and in the denominator we are going to have S plus 1 upon. When we will take the LCM, we will have R1, R2, C and in the numerator we will have R1 plus R2. Okay. So when we keep this R1 and R2, we will take the inverse, then it will become R2 upon R1 plus R2 and here we will have R1 C. Okay, we have just taken the LCM and we have taken the reverse of it. So it is R1 R2 C. The numerator term was R1 plus R2, so we have bring it in the denominator. So here this 1 upon R1C is T, this R1C is T, okay. So R1C is T and this ratio R2 upon R1 plus R2 is alpha, okay. So this is R1C is T and R2 upon R1 plus R2 is alpha. So substituting the value here, we have S plus 1 upon T, and this is S plus 1 upon, this is alpha, this is T, so alpha T. Okay. Now simplify it, we will get E naught S upon EIS equals to, we have S plus 1 upon T. So if we take the LCM, then it will be 1 plus ST upon T, and this will be 1 plus alpha ST upon alpha T. So this will become 1 plus ST upon T, and this is 1 plus alpha ST upon alpha T. So T and T will be cancelled. This alpha, it will goes in the numerator. So our resultant transfer function is alpha 1 plus ST upon 1 plus alpha ST. So this is the transfer function of the phase lead compensating network. Here the alpha, it is the ratio R2 upon R1 plus R2, and it should be less than 1, and T is equals to R1C. Okay. Now if we consider this transfer function, then if we calculate the zeros and poles from this transfer function, 0 can be calculated by equating this numerator part to 0. So we will have 1 plus ST equals to 0. So 1 ST is equals to minus 1, and S is equals to minus 1 by T. So this is 0 of this system. And if you want to calculate the pole, want to determine the pole, so we have to equate this denominator polynomial to 0. So 1 plus alpha ST equals to 0, alpha ST equals to minus 1, S is equals to minus 1 upon alpha T. So this is the pole of the system. So we have 1 0 and 1 pole. If we want to plot or we want to represent these zeros and poles on the S domain, then how we can represent the zeros and pole? 0 is represented by a circle and pole is represented by a cross sign. So it is the S domain, S plane. This is the imaginary axis and it is the real axis, because S is equals to sigma plus j omega. Now 0 is S is equals to minus 1 by T, and pole is S is equals to minus 1 upon alpha T. So we will represent the 0 here. This is minus 1 upon T. 0 is represented by a circle, and if we want to represent the pole, it is represented by a cross sign. So it is our pole and it is minus 1 upon alpha T. So there is one pole and one 0, and it is the pole 0 configuration of the phase lead network. Now from this pole 0 configuration, if you see that this 0 is close to the origin, this point is origin, okay, and hence 0 is nearer to the origin, so this 0 will be the dominating 0. Dominating 0 because its effect will be more with respect to this pole. Okay, in comparison to this pole will have less effect on the system, and this 0 will have more effect on the system. So due to the 0 effect, we can say that from this pole 0 configuration, we can see that so 0 is nearer to the origin as compared to the pole, hence the effect of 0 is dominant, and that is why this 0 is known as the dominating 0. Now due to this dominating 0, the phase lead network, when it is connected in series with the forward path gain, then the phase shift of the system, it increases because this 0 is having the dominating effect on the system. So due to this dominating 0, when the phase lead network is introduced in the system, the phase shift, it increases. Okay. Now, if we want to calculate the maximum phase lead or maximum phase shift introduced in the system, this maximum phase lead is called phi m. And if we want to calculate the value of alpha, then how we can calculate these values? Let's see. We have the transfer function as E naught S This is the transfer function in the S domain. Now let us obtain the transfer function in the frequency domain. So put S equals to j omega. We will get So this is the transfer function in the frequency domain. Now let us obtain the magnitude of this transfer function. So magnitude is given by m, and it will be equals to alpha 1 plus st. So its magnitude will be 1 plus omega square t square. And in the denominator we have 1 plus alpha st. So its magnitude will be 1 plus omega square alpha square t square. So this is the magnitude of the transfer function. And phase angle is represented by phi. This was magnitude. And this phi is given by tan inverse of because tan inverse of alpha, it is a constant, so it will be 0. So only this part and this part, that is tan inverse of omega t upon 1 minus tan inverse of omega alpha t upon 1. So this is the phase angle. Now we have to find out the maximum phase shift. So to find maximum phase shift, that is phi m, you have to calculate d phi by d omega, and then you have to put this d phi by d omega equals to 0. So let's calculate this d phi by d omega. So for this you have to differentiate this equation. So by differentiating this equation, we will get t upon 1 plus omega square t square minus alpha t upon 1 plus alpha square omega square t square. And you have to put this d phi by d omega equals to 0. You have to differentiate this equation with respect to omega. So differentiation of tan inverse of x by y is 1 upon x square plus y square, and then you have to differentiate this term also. So this is the differentiation, d phi by d omega, we have equated it to 0. So here if we obtain, we will solve this, we will get t upon 1 plus omega square t square equals to, bring this part to this term to the right hand side, we will have alpha t upon 1 plus alpha square omega square t square. Okay, let's cross multiply it, we will get 1 plus alpha square omega square t square multiplied with t, and here alpha t multiplied with 1 plus omega square t square. Multiply in the t inside the bracket, we will get t plus okay, or we can say that this t and t, they can be cancelled out, so no need to multiply it inside, we will get 1 plus alpha square omega square t square, and here we will get alpha plus alpha omega square t square. So we will get here 1 minus alpha, if we bring this alpha to the left hand side, and let us bring this side this term to the right hand side, so we will have alpha square omega square t square plus, sorry, this is minus, plus alpha omega square t square. Okay, so here we have 1 minus alpha, from this side take common, so we have omega square t square as common, and we are left with, and alpha is also common, so we are left with 1 minus alpha. So 1 minus alpha cancelled out, we are left with alpha omega square t square. So from here the value of omega square is 1 upon alpha t square. So omega will be 1 upon t under root alpha, and this omega is omega m, because we are calculating phi m, so the frequency will now become omega m, that is maximum frequency. So this is our value of the frequency. Now from the equation of the phase angle, the phase angle equation is phi equals to tan inverse of omega t upon 1 minus tan inverse of omega alpha t upon 1. So if we take tan phi here in this equation, then tan phi is equals to tan phi equals to tan of this whole term. So we will write tan inverse of okay. Now let's obtain tan phi. It will be tan of tan inverse of this equation. So it will become omega t minus this is the value of tan phi. Let us simplify this value. We will take omega t as common. So we are left with 1 minus alpha. And here if we take omega t, omega square t square, and it is alpha. Okay. Now we have calculated the value of omega or omega m as 1 upon t root alpha. And tan phi m, if we calculate, it will be, replace this omega by omega m. So omega m t 1 minus alpha upon now substituting the value of this omega m in this tan phi m. So we will get, this is what, 1 upon t root alpha multiplied with t 1 minus alpha divided by here 1 plus omega m square. So its square will be 1 upon t square alpha. This is t square alpha. So the value of tan phi m, this t square alpha, they will be cancelled out. Okay. And here we are left with 1 upon t root alpha. T and t, they will be cancelled out. So we are left with tan phi m equals to 1 minus alpha upon 2 root alpha. So this is the value of tan phi m. Now from this tan phi m, if we calculate sin phi m is the maximum phase lead. Okay, just remember. So sin phi m will be 1 minus alpha upon 1 plus alpha. And through this, the value of alpha, which is the constant we have introduced, alpha will be 1 minus sin phi m upon 1 plus sin phi m. Okay. So just remember all these formulas for the phase lead network whenever numericals or problems are asked on this phase lead network, then you can directly use this formula. Here omega m is equals to 1 upon t root alpha. Now let us draw the Bode plot for this phase lead network. So if we see the Bode plot, on the Bode plot, this is the amplitude, or we can say the magnitude. This is the zero line. This is frequency. And it is our maximum frequency omega m. This 1 by t was the 0 and 1 upon alpha t was the pole, and omega m is the frequency. So if you see this Bode plot, this is the Bode plot for the phase lead network. It shows that the phase lead network, it allows to pass the high frequencies, but it attenuates the low frequencies. Only high frequency are passed, low frequencies they are attenuated. So this can be used as the high pass filter, that is high frequencies they are allowed to pass and low frequencies they are attenuated. So the Bode plot reveals that Okay, so phase lead network can be used as a high pass filter. It allows to pass high frequencies while low frequencies they are attenuated. So we have studied about the phase lead network. Now let us summarize some of the main points of the phase lead network. The first point is that the phase lead network, it can be used as a high pass filter, as a differentiator. Okay, so we can use this phase lead network The second main point is that, as we have seen that in the phase lead network, the zero is dominant, that is, it is having a dominating zero, and when the phase lead networks they are introduced in the system, that is, they are connected in the forward path loop, so this phase lead network, it increases the phase shift of the system. So this is the second point, that it increases the phase shift. Also, the rise time and the bandwidth of the system is increased. Then phase margin. Okay, so rise time, bandwidth, phase margin, relative stability, the velocity error coefficient, KV, all are increased due to the phase lead network. Whereas the error is reduced due to the phase lead network. Okay, so these are some of the key points or some of the effects of the phase lead network when they are connected in the system as a compensating network. Now let us study about the second type of compensator, phase lag compensator. Now in phase lag compensator, the phase of the output voltage, it lags the phase of the input voltage when a sinusoidal input is applied to the system. So let us draw the electrical network or circuit diagram for the phase lag compensator. Okay. Now let us write the equations for this circuit because we want to derive the transfer function. So if we write the equations for this electrical network, we have EI equals to I R1, I this current and R1 plus I R2 plus 1 upon C integration I dt. This is the voltage, the input voltage, and E naught is the output voltage. It is equal to the voltage across the resistance and the capacitor. So it will be I R2 plus 1 upon C I dt. Okay. So this will become, for deriving the transfer function, we have to take the Laplace transform of these two equations. So let us take the Laplace transform of these two equations. The first equation's Laplace transform will be EIS equal to I R1 IS R1 plus IS R2 plus 1 upon SC, and we have IS. So here we will write EIS So we have these two equations. Now for transfer function, we have to take the ratio of the Laplace transform of the output and the input. So output is the output voltage E naught and input is the input voltage EIS. So the ratio of E naught S upon EIS is what? Here we have R2 plus 1 upon SC. IS can be taken as common, and here we have R1 plus R2 plus 1 upon SC. Again IS can be taken as common. This IS and IS, they are cancelled out, so we are left with R2 plus 1 upon SC Now just like the phase lead network, we have introduced a constant there as alpha. Here we will introduce another constant beta. So the transfer function will become one plus st upon 1 plus s beta t, where beta is R1 plus R2 upon R2. So in phase lead network, we have introduced the constant alpha. Here we have introduced beta. So our transfer function is 1 plus st upon 1 plus s beta t. Here t, that is the time constant, t is R2C. Now again drawing the pole 0 configuration of this phase lag network. Here we have 0 as 1 plus st equals to 0. So st is equals to minus 1. S is equals to minus 1 by t. This is the 0. And pole is 1 plus s beta t equals to 0. So s beta t equals to minus 1. S is equals to minus 1 upon beta t. This is 0. This is the pole of the system. So let us represent this 0 and pole in the S plane. So we will have this is the S plane, j omega x's and sigma. So here we have minus 1 upon beta t as the pole and 0 is minus 1 upon t. And this is the origin. So if you see this pole 0 configuration of the phase lag network, you will see that this pole is close to the origin as compared to the 0. So here this pole will be the dominating pole. In phase lead network, we were having dominating 0. Here we are having dominating pole. So here in the phase lag network, we have a dominating pole because it is nearer to the origin as compared to the 0. So its effect will be more, and due to this dominating pole, the phase shift is reduced when a phase lag network is introduced in the system. Okay, so it is the effect of the phase lag network. Then it is introduced in the system, the phase shift is reduced. Okay, now similarly, like phase lead network, we have calculated the maximum phase lead, and here we will calculate the maximum phase lag which this phase lag network can introduced in the system. So maximum phase lag introduced, it is represented by again phi m, and we will calculate here beta also. So maximum phase lag is here represented as phi m and beta. So let's see how we can calculate. We have the transfer function of the phase lag network as this is the transfer function. Now to obtain it in the frequency domain, we will put S equals to j omega. So E naught j omega upon EI j omega equals to this is the transfer function in the frequency domain. Now let's calculate the magnitude of this transfer function. So magnitude is represented by m, and it will be equals to under root 1 plus omega square t square upon under root of 1 plus omega square beta square t square. This is the magnitude of the transfer function. And phase angle is phi. So phi is given by tan inverse of omega t upon 1 minus tan inverse of omega beta t upon 1. This is the phase angle. Now we have to find out the maximum phase lag. So we will again differentiate this phase angle equation with respect to omega, and then we will put d phi by d omega equals to 0. So to find phi m, put d phi by d omega equals to 0. So let's calculate d phi by d omega. It is t upon 1 plus omega square t square minus this is the d phi by d omega. We have differentiated the phase angle with respect to omega and we have equated it to 0. So let's solve it. We will have 1 plus omega square t square equals to beta t upon 1 plus this t and t, they are cancelled out, cross multiply, we will get okay. Then bring this to this side, 1 minus beta, we will have beta omega square t square minus 1 minus beta, here take beta omega t, omega square t square as common. So we are left with 1 minus here beta. So 1 minus beta, they are cancelled out. So 1 equals to beta omega square t square. So from here the value of omega is 1 upon, we have beta t square, so it will be t under root of beta. Just like phase lead network, there we have obtained 1 upon T root alpha. Here we have obtained 1 upon T root beta. So this omega is now omega m, that is the maximum frequency. So its value is 1 upon T root beta. Now from the phase angle equation, we have phi equals to tan inverse, okay, that equation for the phase angle we have obtained. So now we are taking tan phi, okay. So tan phi will be tan of the phase angle The steps are same just like the phase lead network. Okay, so here the tan phi is equals to take omega t as common, so we are left with 1 minus beta upon 1 plus omega square beta t square. This is tan phi. Now we have omega equals to omega m equals to 1 upon t root beta. We have calculated here. So just replace this omega by omega n. So this tan phi, it will now become tan phi m. Now we have the value of omega m as 1 upon t root beta. So substitute the value of omega m in this equation and let's calculate tan phi m. We have omega m 1 upon t root beta multiplied with t 1 minus beta upon, here we have 1 plus square of omega m, so it will become 1 upon t square beta. Cancelled out, t cancelled, so tan phi m is 1 minus beta upon 2 root beta. This is 1 plus 1, so it is 2, and this beta will come in the denominator, so 1 minus beta upon 2 root beta. This is the value of tan phi m. Now if we calculate sin phi m from this, then its value will be 1 minus beta upon 1 plus beta. Again we will have all the formulas like tan phi m, sin phi m, then omega m, it is 1 upon t root beta. The formulas are same, just you have to replace the alpha by beta in the phase lead and phase lag network. Now from here the value of beta will come out to be 1 minus sin phi m upon 1 plus sin phi m. So we have tan phi m, sin phi m, beta and omega m. Now let's draw the Bode plot for this phase lag network. At phi m, that is the maximum phase lag, the frequency is omega m, and this is the pole 1 upon beta t, and this is the 0 1 upon t. So if we see, this difference is 20 log beta. This is the magnitude. Okay, so if we see from this Bode plot of the phase lag network, It reveals that the phase lag network, it allows to pass the low frequency but it attenuates high frequencies. So it is allowing the low frequencies, so it can be used as a low pass filter. Okay, so this phase lag network, it can be used as a low pass filter. It is allowing to pass the low frequencies and it attenuates high frequencies. Now let us study some key points of this phase lag network, that what are the uses or what are the effects of this phase lag network. As we have seen that the phase lag network, it can be used as a low pass filter. Second point is that the gain crossover frequency is increased, bandwidth is decreased, and phase margin is increased, response becomes slower. So these are all the effects of the phase lag network. So bandwidth is decreased, response is slower, speed of the system is decreased, and when this phase lag network, it is introduced in the system, the phase shift is reduced. So these are the characteristics of the phase lag network. Now let us study the third type of the compensator, phase lag lead compensator. Now phase lag lead compensator, it is nothing but a combination of the phase lag and the phase lead network. Okay, so why we are using this phase lag lead compensator? Because if we want fast response and good static accuracy, then we will use this phase lag lead compensator. So what a phase lag lead compensator does, it if we want to get fast response, good static accuracy, and it increases the low frequency gain, improves the steady state. So if all these characteristics we want in the system, then we can use the phase lag lead compensation. Now let us draw the electrical circuit diagram for the electrical phase lag lead compensating network. So its circuit diagram will be, it will be a combination of the phase lag and the phase lead network. So here we will have the parallel combination of the capacitor and the resistor, and here we will have the series combination of resistor and the capacitor. Okay, As it is the combination, so its transfer function will be the product of the transfer function of phase lag and the phase lead network. So we have already obtained the transfer function of phase lag and phase lead network. We will just multiply them and then we will obtain the transfer function of this phase lag lead compensator. The transfer function of phase lead network is alpha 1 plus S T upon 1 plus S alpha T, and the transfer function of phase lag network is 1 plus St upon 1 plus S beta T. For simplification, the time constant for the phase lead network we will mark it as T1, and the phase this time constant due to the phase lag we will take it as T2. So this is alpha 1 plus St1 upon 1 plus S alpha T1, and here we have 1 plus St2 upon 1 plus S beta T2. So this is the transfer function. Here we have T1 as R1 C1 and T2 as R2 C2, and these constants alpha and beta, their multiplication is equals to 1. So this is the complete transfer function of the phase lag lead network. Now from this transfer function, if we draw the pole 0 configuration of this system, then it will be like, so if we draw the pole 0 configuration of this phase lag lead network, the pole 0 configuration will be like, here we have the zeros as S equals to minus 1 upon T1, S equals to minus 1 upon T2. Poles are S equals to minus 1 upon alpha T1 and S equals to minus 1 upon beta T2. Okay. Now here we will draw the poles and zeros. We will represent them in the S plane. Here we have first is the pole due to this phase lag network. Then we have 0, then we have again a 0 and pole. This pole is this minus 1 upon beta T2, then minus 1 upon T2, the 0, then 0 due to this phase lead network minus 1 upon T1, and this is 1 upon minus 1 upon alpha T1. Because in the phase lag network we have the pole as the dominating pole, and in the phase lead network we have the 0 as the dominating 0. So if you see, this is the due to the lag network, and this is due to the lead network. So the overall effect on the system will be due to the effect of, or the combination of the effect of these 4 poles and zeros. Okay. Now if we draw the Bode plot of this system, then Bode plot will be like, this is omega, so this is the Bode plot of the system. Now through this Bode plot you can see that it is allowing this phase lag lead network, it is allowing a certain frequencies only. Okay, low frequencies and high, only a band of frequencies it is allowing, so it can be used as a band pass filter. And we can write the characteristics of this phase lag lead network as that it is used where fast response as well as better steady state accuracy is desired. Also, settling time is reduced. Phase margin can be adjusted. Also, the bandwidth of the system is increased. So these are the combined effect of both the phase lag and phase lead networks. So in this video we have studied about the compensators, why compensators are used in the control systems, and we have studied the three types of compensators: phase lag, phase lead and phase lag lead network. Okay, so I hope this video is clear to you. Thank you.